6.1 is entitled Projectile Motion. Projectiles, it's when you throw something in the air, basically. So you got a guy dropping something, throwing it straight up in the air, or you throw it at an angle. Today we're going to specifically talk about throwing it at an angle. We've already talked about dropping things and throwing things up in the air. We've all played Angry Birds. Maybe we've all gone off a high dive, played some basketball. I have a motion diagram here of a yellow ball and a red ball. A red ball is being dropped, but I want to focus primarily on the yellow ball. This is a yellow ball being kicked off by something, and we want to look at the motion because to understand projectiles, there's two main ideas. And just to kind of show you these ideas, what I'm going to do is I'm going to put a vertical line through every single ball in this picture. So in my motion diagram, the key to it is you have to take pictures at equal time intervals, and I want you to just see if you can see a pattern that emerges as I analyze this motion in the x-axis, in the x direction. So how does this ball move left and right? By drawing the vertical lines, you'll be able to tell exactly how it moves left and right. Take away the picture now, and you see how these lines are all evenly spaced? That says one really important idea, and this is important idea number one about projectiles. Main idea number one, they move left and right. Sometimes we call that downrange at a constant speed. Constant speed. Huge. That's very huge. Next thing, let's look at how they move up and down. So I'm going to get rid of all these guys. Now I'm going to draw a horizontal line through every ball and see if we can see a pattern emerging here. You can kind of start to see the pattern already. It looks like every one is a little bit further than the one before. The spacing is getting larger. Now, this is because of gravity. Gravity accelerates things towards the center of the earth, and you can see that this is moving up and down. It's accelerating, so the spacing is going to get larger and larger with each individual one. And I can get this out of the way, and you can see the spacing at the beginning as it gets farther down. Every single time it gets bigger and bigger and bigger. So this brings us to important part number two. They move up and down, well, at a constant acceleration. Acceleration. And that acceleration is 9.80 meters per second squared. Just like the constant speed is whatever the speed you fire it with. So you can have different speeds, but it's really important that they move up and down at a constant acceleration. They move left and right at a constant speed. Now, here, let me show you a couple videos that I found on YouTube in my days of surfing the internets that kind of exemplify a couple of this stuff. They're actually pretty funny. The first one I just found recently. It's from a B-52 bomber going on a practice bombing run over the South Pacific. And you see the bomb bay doors opening up, and it's going to drop these bombs. And the bombs, they move forward at a constant speed. So when these things drop, they stay right below the plane. So they're going to drop here, and look they'll stay exactly straight below the plane the entire time. See all these bombs? You can still see them as they're falling. And then all of a sudden, boom, they come in contact with their practice bombing run. Isn't that neat? Moving forward at a constant speed. Another one, there's some kids that were being kind of dumb, and they thought that they'd fly a bowling ball off of a ramp. But what they don't understand is that the projectile, it's not going to go, it's going to go the same speed as the car. And there's a crosswind. You can't hear it in your video, but there's a wind that blows the bowling ball over top of the car. So the car moves downrange at the same exact velocity as the bowling ball, and it ends up hitting it. The last one, it's from Mythbusters. It's really neat. What they did was they took the question was, what if we took a cannon that shot a ball at 60 miles an hour, pointed it out the back of a truck that's going 60 miles an hour in the opposite direction, and you fire it. So they're firing this thing at 60 miles an hour backwards, but then they're traveling 60 miles an hour forward. What does it look like? And check this out. It's just incredible. Watch this in slow motion. The speed vectors totally cancel each other out, and that thing falls like straight down. Amazing. So the next picture I've got here, this is just kind of showing you the projectile motion. Like you've got something fired, and you can see that the velocity, they kind of show the velocity vector. It's the same length every single time in the x direction, but in the y direction it gets bigger and bigger and bigger. It's accelerating. So here, let's kind of apply this to an actual problem. Can we exploit these facts to solve an actual physics problem? First of all, flight of a ball. It says a ball is launched at 4 meters per second. I'm assuming this is level ground at 66 degrees. So I'm firing it with an initial velocity of 4.5 meters per second and an angle of 66 degrees above the horizontal. What's the maximum height and the flight time? So here's the steps to solving any physics problem that involves projectiles. Step 1, you break it into its x and y components. Sometimes called the horizontal and vertical. So what I'm going to do, I'm going to write horizontal and I'm going to write vertical. Horizontally, I know this thing moves at a constant speed. And here I know that it accelerates. So when things accelerate, they can have an initial velocity, a final velocity, acceleration, time, and distance. When they're moving at a constant speed, the initial and the final velocity are the same, so we just call it v. The acceleration is 0. There is still time and distance. So this velocity right here, this velocity is not horizontal, nor is it vertical. What you're going to have to do is find the horizontal and vertical components of this velocity. So what you're going to do, got to find this and this. We'll call this the y, and we'll call this the velocity in the x direction. So we're going to end up using sine and cosine. So we'll say the sine of 66 degrees is equal to the opposite, which is the velocity in the y, divided by the hypotenuse, 4.5. So I take 4.5 times the sine of 66. I don't know if this is going to work. There we go. 4.5 times the sine of 66. And we get 4.11. So the velocity in the y direction, 4.11. And then we'll take the cosine of 66, and that's going to be the adjacent, which is the velocity in the x, divided by 4.5. So I'll take 4.5 times the cosine of 66. So 4.5 cosine 66. And I get 1.83. So the velocity in the x is 1.83. The velocity in the y is 4.11. So This y is the vertical initial velocity. This x is the horizontal velocity. Now, I'm going to exploit this spot right here. There's something special about that spot. At that spot, it's not moving up or down, so the vertical final velocity is 0. The acceleration is negative 9.80. It's negative because I said that the velocity in the y was positive, so that means that the acceleration is down, so it has to be negative. Now, here I can figure out the flight time because, boom, I've got a bunch of stuff. I now know. So after we break it apart, use equations to find unknowns. So I'll find the time. I think I'll do VF equals VI plus AT. Final velocity, 0. Initial velocity is 4.11. The acceleration, negative 9.80. And the time, t. So what I'm going to end up doing is taking negative 4.11 divided by negative 9.8. 4.11 divided by 9.8. And I get 0.42. So my time is 0.42 seconds. Now be very, very careful. Here's where a lot of people make mistakes. Sometimes we double it. I'll show you what I mean. Since we use this special spot, this is the time it takes to get right there. So when the question asks us, how long is it in the air for? Since we used this spot, we gotta double our time. So the time that's in the air, sometimes we call it the hang time, is 0.84 seconds. Done. The next thing, it wants to know how high. That's a vertical distance. So now I'm going to go after this guy. It's a vertical distance. So I think you can do whatever you want. Maybe I'll use this equation. D equals VI t plus 1/2 AT squared. My initial velocity is 4.11. The time, now we have to be very careful. Since the maximum height's right there, you're going to use the time for right there. You can't use 0.84, and otherwise you're going to find that this d is going to equal 0. And you'll be like, what? Well, that's when it hits the ground. So you got to use 0.42 plus 1/2 negative 9.8 0.42 squared. And you run this through your calculator, and it's going to come out to be, I think it's like 0.86 or something like that. It's really small. So 4.11 times 0.42 minus 0.5 times 9.8 times 0.42 squared. 0.86. And the first time I did this, I was like, this doesn't make sense. It's not even going to go 1 meter in the air. Apparently not. This must be a very slow pitch for it to only go 0.86 meters in the air. So, how high did it go? 0.86. What's its flight time? 0.84. Now, if it asks how far, if it had asked me how far, that would be referring to this, a horizontal distance. How far did it go? And for us to do that, here's the trick. The time is the same horizontally and vertically. So if I want to know how far it goes right here, I already know how much time it took to get there, and that's 0.84 seconds. See how these are the same? So then I just use velocity equals distance over time. my velocity being 1.83. Don't know the distance, but I take 0.84. So if I take 1.83 times 0.84, I get 1.5. This only went 1.5 meters. So now I know everything there is to know about this problem. Let's break it into its x and y components. It moves left and right at a constant speed, and it moves up and down, accelerating. Now, there's a whole bunch of like scenarios you could come across, as far as I know. Like, meaning that you could fire something straight up in the air. You could fire it at an angle. You could fire something horizontally. You could fire it at a downward angle, or you could fire it straight down. And they're all exactly the same, and they're all different. Let me show you how they're the same. For instance, let's say that in every case they're launched at 10 meters per second. I'm going to give these all names. I'll call this case 1, I'll call this case 2, I'll call this case 3, I'll call this case 4, I'll call this case 5. First of all, in case number 1, I'm launching it completely vertical. So the vertical initial velocity is 10 and the horizontal velocity is 0 because it's not going left or right at the very beginning. It's only going straight up. And it's the exact opposite over here. Well, not exact opposite, but case number 5, the initial speed is -10 and the velocity horizontal is 0. So I think what I'm going to do in every case, I'll just say up is positive just to keep it all the same. Look at case 3. This one, though, it's being launched completely horizontally and there's no vertical component initially. In case 2 and 4, in these cases, you're going to have to find the x and the y components. And let's just, for argument's sake, say it's 6 and 8. So we'll call this 6 and 8. So horizontally, the velocity is 6. Vertically, the velocity is 8. Over here on number 4, horizontally, it's 6, but here it's -8. See how the positives and negatives kind of like they work to your advantage? All right. Now, since this is on Earth, every single one of these accelerations is going to be -9.8 vertically. Let's just say, for argument's sake, that every one of these cliffs is 100 meters tall. The distance is going to be, now this is crazy, it's -100. Because you end up down here, because you started here, you're going in the negative direction. So the displacement, it's where it starts to where it ends. Who cares that it goes up to begin with? In every one of these cases, it's going to be -100. Even if you launch something like on flat ground, the displacement, if you wanted to, you could say the displacement equals 0 because it starts and ends at the same spot. You could solve for time and get the hang time. So that's kind of a rabbit in the hat you could utilize. Other things, just I think that these are kind of the initial conditions. If you wanted to, you could use this spot and the final velocity there would be 0, but if you're going to use that spot, you can't use -100 as the displacement. You could use these 3 things to figure out how high it went in the air, and you could figure how much time, but you're not going to be able to use -100 for your displacement, and the final velocity is 0. If you're going to use these 3 things and you solve for the final velocity, that's the velocity with which it hits the ground. A lot of people think that the final velocity is 0. It's not true. If you're going to use -100, it's the speed with which it hits the ground. Over here, if you solved this one, you use these 3 guys and you solve for the final velocity. When this guy strikes the ground, it's moving forward and it's moving down this final velocity is going to be this piece, and it's going to be moving forward at 6 because remember it moves forward at a constant speed. Let's see. Same with this guy over here in case 3. The final velocity, this thing's going to be moving forward and down. It's going to be moving forward at 10 because remember it stays going forward with the same speed every time. Again, this one is going at 6, so they have similarities between all of them, but they're differences. So you just kind of have to know what's going on when you set the problem up, because then all you got to do is use those big 3 equations, or velocity equals distance over time, to solve for your unknowns.